Continuing our idea of a series expansion around an ordinary point. These are two examples in the text. Rather than me go through them, I want you to read them. But the first one is called Airy's equation. It happens to be a classical equation from mechanics used a lot of places and was generalized. What's interesting about this particular equation is that the solution isn't a very nice closed form. It's not truly related to a factorial. There's a nice factorial in there, but it's actually better expressed in terms of the gamma function, which is much more complicated, unfortunately. So I would expect us to just end up writing the first few of them as best we could and not looking for a general formula. We got lucky with the ones we did yesterday, where we could come up with a specific general behavior. In this one, before I even start solving it, I got a question for you. What's the radius of convergence around the ordinary point 0? The roots are plus or minus I, so the distance from the origin to that is 1. Exactly. So my radius of convergence is 1, because the roots here are I, and I look for the distance to the nearest 1. That's how I find the radius of convergence for my power series. If I actually work this one all the way out, one of the solutions has ck equals 0 for all k bigger than or equal to, I think it's 2. Which means we end up with a polynomial. The other one happens to have a power series expansion that goes off to infinity. But this one actually just terminates. So once we find, hey, this is 0 from here on out, that means that solution's a polynomial. That makes my life a lot easier. The important part is designing this recurrence relation for the coefficients. So here's a problem we'll work through from scratch. Again, I'm going to make the assumption that I'm going to start from 0. This happens to have a radius of convergence that's infinite in this case, because the coefficient of y double prime is 1. I don't have to worry about anything being a singular point. This has no singular points at all. So here are my series to start with. So let's put those in for y double prime, y prime, and y respectively. Oops, as I realize, I think I made a copy error. Hang on a second while I check. I did. Click. About to say, this doesn't look right. I should have not have two y terms. I should only have one y term. It would be ideal if I could gather all my like terms so I had one power series on the left-hand side. But to do that, I need to do two things. I need to take these pieces, the x squared and the x, from outside the series into the series. And then I need to re-index appropriately. So everything is in terms of the same power. So let's start by moving these in. So in the middle sum and the third sum, I increment my powers of x appropriately. I'm multiplying the x squared, that takes me from x to the n minus 1 to the x to the n plus 1. I'm multiplying the x, I go from x to the n to the x to the n plus 1. So I have different powers everywhere. This is a problem. I really want everything to be the same. I'm going to do three different reindexings. Over here, I'll do a U sub to set k equal to what? And in these two? Right. So I know I'm going to do k equals n minus 2 here. And for these two, I'm going to do k equals n plus 1. I know I said yesterday I prefer to do them one at a time. I'm going to do it in one fell swoop here. When I do this, for this first sum, my limit is now k equals what to infinity? Zero, because I'm subtracting 2. So if I have an n, that's a k plus 2. If I have an n minus 1, that's a k plus 1. Cn, k plus 2, x to the k. What happens in the second sum? Where's this sum start? I went the other way. It starts at 2. So where I have an n, I replace it with k minus 1. And then I'll get c k minus 1 x to the k. What's my third sum? We're starting at 1 this time. And so it'll be, again, ck minus 1, x to the k. With me so far on the reindexing? I'd like to gather my like terms, because that's the appropriate thing to get one power series. But now I have another problem that's a little different than the problem I had before. They're all in x to the k, but they don't all start at the same place. This one starts at 0, this one starts at 2, this one starts at 1. Crap. If I really want to start gathering like terms in the series, I need them all to start at the same place. So I need to try and pull out things from the series that aren't in the same place. The highest lower limit is 2, right? So I want to take out everything before 2 from this series. And I want to take out everything from before 2 in this series. That way, all of my sums will start at the same lower limit. So now I have to go back and I have to look at that first sum. And in that first sum, we start with k equals 0, right? This one. So I need to think about the numbers that are less than 2. That's 0 and 1 in that sum, yes? So write down what happens when k is 0. What do I get when k is 0?
Two CK plus 2. Oh, you're saying 2 CK 2. Okay.
If k is 0, I get 2 times C2 times x to the 0. Right? That's from that first sum. But I also have to pull out k equals 1. So what do I get when I put in a 1?
Six, 63. 6.
And then I'm going to leave all the rest of it, k equals 2 to infinity, k plus 2, k plus 1, ck plus 2, x to the k. Right? I haven't touched any of the rest of it because that's 2 and bigger. The middle sum is 2 and bigger. So I don't have to worry about anything for the middle sum. And now let's look at the last sum. What do I have to pull out? Because it'll be k equals 1, right? So it'll be C0 x to the 1 plus everything from 2 on. So first sum, second sum, third sum. See how all of these start at 2 now? And here's everything that was before 2. Now here's the best part. I can gather my like terms. I even lined stuff up for us. This is the only x to the 0 term. This is the only x to the first terms. Everything from 2 up is in here. So really, when I combine my like terms, I get 2c0 plus c0 plus 6c3x plus a giant sum. With me on the giant sum? Okay, so what's the giant sum? Well, all I have to do is add all the coefficients here. K plus 2, k plus 1 times ck plus 2 plus k minus 1, ck minus 1 plus ck minus 1 times x to the k. I ran out of room there right at the end. And that's equal to 0. Wait a second. I made a copy error. Somebody catch my copy error.
But next to the K and this.
Here?
Oh, and
No, I made a copy error from here to here. It's not 2c0, it's 2c2. Now, in order for this power series to be equal to 0, every single one of these coefficients must be 0. What do I know about C2?
zero.
Aha! For this to be 0, 2c2 has to be equal to 0, therefore C2 is 0. I also know that has to be equal to 0. So C3 is negative 1/6 C0. And then this thing has to be equal to 0. Wait a minute. These are both ck minus 1, aren't they? So really, k plus 2, k plus 1, ck plus 2, plus how many ck minus 1s? There's k minus 1 of them here, and there's one more there. So there's k of them. That has to be equal to 0. So ck plus 2 is minus k ck minus 1 over k plus 2 k plus 1. And that's only good for k bigger than or equal to 2. Now, if I start pushing out and trying to figure out all of the c's in my recurrence relationship, I could do everything in terms of C0 because I have C0 over there as a free choice right here. Yes? C0 is whatever I want it to be. I know C2 is 0. What about C1? C1's not mentioned here, is it? As a matter of fact, the only place I'm going to see C1 is when I put in k equals 2 right here. Yes? That means C1 is also a free choice. Since C0 and C1 are free choices, let's choose them to be easy numbers. As a matter of fact, I'm going to do two different sets of choices. My first set of choices is going to be C0 is 1 and C1 is 0. My second set of choices is going to be exactly the other way around. C0 is 0, C1 is 1. If we go back and look at the example we did yesterday, this breaks up the evens and the odds. This makes my polynomial, my power series expansion, easier to find because a whole bunch of stuff is equal to 0. Let's see if we can work our way through what happens in one of these sets of choices. We'll do them both eventually. So which one do you want to start with, number 1 or number 2? So if I start with number 1 here, well, if C0 is 0, oh, sorry, C0 is 1, C1 is 0. I know C2 is 0 because we have that explicitly. What's C3? Oh, we did that right here. C3 is negative 1/6 times C0. What's C4? Ah, C4 is going to come from here, isn't it? So that's going to be minus 2 times C1 over 4 times 3. But what's C1?
Yeah.
Ah, well, that makes that 0. What's C5? That's going to be in here. If this subscript is a 5, what's the value of K? So it'll be negative 3C3 over 5 times 4. What's C3?
Should it be C2?
Oh, you're absolutely right. Yes, good catch. What's C2? Hey, that makes my life easy. Hey, wait a minute. 1, 0, 0, negative 1, 6, 0, 0. I bet this pattern is going to continue, and I'm only going to get every third number. What's C6?
Negative 2/3. That's the top.
So wait, let me write it out. It's negative 4C3 over 6 times 7, but C3 is negative 1/6, so I get 2/3 on the top and then 42 on the bottom. Wait, no, that's not 7. That's 5. I can do arithmetic. All the things I'm going to screw up, it's adding. So that's 2/3 over 30. Wait a minute, that's 1 over 45. And yes, C7 is 0. And C8 is 0. So if I wanted to, I could start writing and I could tell you that my first solution is 1 minus 1/6 x cubed plus 1 over 45 x to the 6th. And if you wanted to get C9, you could get C9. And if you wanted to, you could get C12, and you could keep going, couldn't you? So now it's a question of how many terms do you really need? Remember, our power series can be expanded as far as we want. And if I don't recognize this as some particular series, like I recognized cosine yesterday, well, then I'll just leave it like this. It works. What happens in option 2? Well, now we have it the other way around. C0 is 0, C1 is 1. What's C2? The equations we are using don't change. I'm still using this same relationship right here. C2 is 0. What's C3? Because, well, I should check. For me to use C3, I've got to do this, right? So C3 is -1 C0 over 3 times 2, but what was C0? So we did get a 0. -1/6 C0, right? Right, yeah, you're exactly right, but notice it worked. I could do it here or I could do it there, because this is true for k bigger than or equal to 2. That works, but it matches. It better match, or we would have summed up royally. So you're right, it does look like it's going to be every third term again, which means C4 should give me something. C4 is going to give me well, if this subscript is 4, then k is a 2. -2 C1 over 2 plus 2 is 4. 2 plus 1 is 3. That's -1/6 times C1, but C1 is 1. C5. Okay, wait a minute. C5 is -3 C2 over stuff, but C2 is 0. C6. If that's 6, then k is 4, so I get -4 C3 over stuff. And the reason I don't care about the stuff is because C3 is 0. Every third, you were right, Cody. What's C7? If this is a 7, then k is 5. -5 C4 over 5 plus 2, 5 plus 1. So that's -5 times -1/6 over 42. Well, that's disgusting. 240 and 252. 5 over 252. And again, I can now write with assurance y2 of x is 1x, because that's C1, plus -1/6 x to the 4th, plus 5 over 252 x to the 7th, and so on. And I've got my both of my solutions based on my choices of C0 and C1, right? Now, really, since I chose C0 to be 0 and C1 to be 1, I could put a capital C in front of this, couldn't I? If I picked C1 to be any other number, there'd just be a C1 in front. Same thing with C0. I chose C0 to be 1. I could put C1 and C0 in front of that. Hey, doesn't that look like our solution C1 times Y1, C2 times Y2? That's exactly what we got when we did our solutions. In general, we get C0, Y1 of X, plus C1, Y2 of X. Because C0 and C1 are free choices. I just picked 0, 1 to make my life easier. Questions? How do we find C0 and C1 here? If I was doing this without power series, how would I go back and find C0 and C1?
The X of C and Y of C.
That was my complementary or corresponding homogeneous solution for the systems when I had non-homogeneous stuff. This was still equal to 0, so it's still homogeneous. That's a good place to start, but I'm actually looking for the coefficients for the numbers that we came up with. Go back to the first exam. We'd solve these problems, we'd get a plus C. How did we figure out what the plus C was? I need an initial value of some type, right? This is a second order differential equation. I should have two initial values. If I have initial values for an initial value problem, usually it's y of 0 and y prime of 0, right? Hang on a second. What happens when you plug 0 into that power series? Unfortunately, not everything is 0. Because remember, this power series is that, right? What happens when you put in 0? Wait a second. What's y prime? Take the derivative of this thing. What's y prime?
C1 wrong.
So what's y prime of 0? See what I meant by their free choices? They're the choices in our initial conditions. You sneaky mother, or you hid the initial conditions from me. They're C0 and C1. I don't actually get any sort of forced choices here. They're all based on my initial conditions. Questions? Cody, your statement about XC reminds me that there should be an XP for a particular solution if I had a non-homogeneous bit, right?
Mhm.
So if I had this, doesn't help if you can't see it because I wrote off the bottom of the page. If I have this sort of garbage, then I need to figure out what to do with this f of x. But fortunately for you, that's actually really easy. I convert f of x to a power series also. And then I move it from the right side to the left side. And then it's equal to 0. So basically, I'm going to do the same thing. They'll just be extra bits on the right-hand side. Now, in order for this to work, the power series for f of x has to exist at our x0, our ordinary point. So f of x can't be singular at 0. If it's singular, then we have a problem, and it's much uglier and less pleasant. Now, I have to write a power series for f of x, means I need to remember those basic power series, the Maclaurin series that we have for sine and cosine and e, and the ones in chapter 6, section 1, the ones we used in Calc 2. Or I have to be able to write it, Mia, the way you were telling me yesterday, geometrically. This also works if P or Q aren't polynomials. What if I had something like this? Other than me wanting to run screaming from this picture, I could try and use some sort of variation of parameter idea here and hope for the best. But I think that would suck because that's sine of x. That's not a nice coefficient. That's disgusting. But if y is a power series, then I can say, hey, wait a minute, I have that power series for sine of x. Which is the same as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial and so on. I could actually multiply these two power series together, as disgusting and gross as that thinks. So I could write this piece as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial times c0 plus c1x plus c2x squared plus c3x cubed. And if I multiply all that garbage out, then I would have a power series that I could use for that middle piece. I am going to be the first person to tell you that this just made the problem about 3 times longer than it needs to be. It's gross and disgusting and not pleasant, but it works. And it is actually the easiest way to solve this particular problem. Example 8 on page 254 walks through another one like this. But I'm not going to do that here. Questions? Okay, 2 important things. The advent of working on a computer makes this much faster. Power series expansions on computers are literally 10-second problems. Now, 10 seconds on a computer is like a week for me, so I'm pretty sure I want to double check what they do and make sure they get it right, or at least that I understand what the hell happened. But all of what we have done is possible because I was working at an ordinary point. Here is another power series problem. If I wanted to do what we were just doing, I would say, oh, well, I'm going to let y equals some cn x to the n equals 0 to infinity. What is the radius of convergence? Oh dear. What's the problem here?
Need to get y over x.
Yeah.
So that's y.
And 1 over x means that my singular point is 0.
Yeah.
But that means that the center of my power series is a singular point. I can't do this. I cannot always put a power series at a singular point. No, complex variables question. When I talk about having singular points, singularities, what kinds of singularities are there? There are three kinds. And you had to know them to use your big theorem to do integrals. Yes, I know. I wouldn't be pushing you if I didn't know that Leah had literally just tested you on this. Yes, I need them to be isolated, but in isolated singularities.
Oh, zeros, poles,
Poles, essentials,
yes,
and removable.
yes.
Poles. Poles have order, right? A pole has an order. It turns out that it is exactly this idea that I can use to classify the singular points for a differential equation. Here's our usual second order differential equation. I didn't even write it in P and Q. I just wrote it with A2. But I could just as easily say, oh, right, this is y double prime plus P of x y prime Q of x y equals 0. Same differential equation. We say that x0 is a regular singular point. If it's a pole whose order is less than 2. But that doesn't make sense to anybody who hasn't done any complex variables. So let me write it out the easier way. If when I multiply P by x minus x0 and Q by x minus x0 squared, those are both analytic. So singular points are either regular or irregular, depending on the way I can look at the function once I add in this extra multiplication. I beg your effing pardon. I need some examples or this doesn't make a damn bit of sense. Hang on. Here we go. X cubed y double prime plus 4x squared y prime plus 3y equals 0. Let's rewrite that for P and Q. What do you get for P of x and Q of x?
What do you actually get for On the X. Q of X is 3 and then the X.
Okay, so the first question I have, what's my singular point? Aha. So I want you to take P of X and multiply by X. I want you to take Q of X and I want you to multiply by X squared. What's X times P of X? And 4 is a perfectly differentiable, nice function at 0, isn't it? I like this. What's X squared times Q of X?
3.
Oh, crap. Why is that a problem? It's still undefined at 0, right? And that means that X is not just a singular point. X equals 0 is an irregular singular point. This function, 3 over X, is not nice at 0. It's effed up at 0. Same starting question. What are my singular points? Exactly. Because that's where this is 0. Great, love it, wonderful. I need P, I need Q. I'll rewrite this to give me P and Q. So far, so good? But algebra. Something nice happens in both P and Q. What can you tell me about that denominator? Right, x plus 3 times x minus 3, the whole thing squared. I'm actually going to write it as x plus 3 squared, x minus 3 squared, right? Each piece is squared. Wait a minute. What happens here? So I really get 1 over x plus 3, x minus 3 squared, and 2 over x plus 3 squared, x minus 3 squared, because nothing canceled in that one. Now there are two different singular points. So I need to ask you about each one. Do you want to do 3 or -3 first? 3? Okay. If I'm going to do 3 first, I need to multiply by x minus 3 here. I need to multiply by x minus 3 squared here. So when I'm looking at x equals 3, it's x minus 3 times p of x, and it's x minus 3 squared times q of x. What do I get?
Yeah, x minus 3. Yeah. Or q, or q of x.
Hang on. Before I go any further, what happens at 3 there? That blows up, but that does not work. There's my frowny face. Right there. Right here. This tells me what about x equals 3? It's irregular. Now do the same thing for x equals -3. For x equals -3, we're going to look at x plus 3 times p of x. We're going to look at x plus 3 squared times q of x. What are these two functions?
X minus 3 square root. Both of them.
Now, remember, we're looking at x equals -3. Are those okay at -3? Yeah, they're perfectly fine there. That's continuous at -3, which makes x equals -3 what kind of singular point? It's regular. So one differential equation can have both kinds. Some that are regular, some that are irregular. That's acceptable. As a matter of fact, I can make a general statement. If I can write if I can write P of X as having no more than one factor of X minus X0 in the bottom, and I write Q of X as having no more than two factors in the bottom. See these stars up here on the top? I'm using that to mean that that is not zero at X0. So in the one that was regular, Cody, that was X equals -3, right? The numerators were both zero, weren't they? Sorry, we're both one.
Yeah.
So it worked. We got rid of our X plus 3 and our X plus 3 squared. But that only works when I can write out a polynomial and factor, and all sorts of nice things happen. It is possible to have complex singular points. If I rewrite that, I'm going to get y double prime plus -2x over x cubed plus 4x plus y prime plus 6 over x cubed plus 4x y. Wait a minute. How does that denominator factor? Careful. So that's going to be x minus 2i, x plus 2i. That's got complex roots in it. Which really means y double prime plus -2 over x minus 2i, x plus 2i, because the x on top will cancel with one x on the bottom, plus 6 over x, x minus 2i, x plus 2i. I can tell you right now, without doing any additional work, that all three of these points are regular. Why is that true? Not actually because of I. It's actually because of the exponents of the terms in the bottom. The highest power involved for x or x minus 2i or x plus 2i in the bottom here is 1. The highest power needs to be less than or equal to 2. Well, the highest power is always 1. That means we satisfied this idea, so they're all regular. Example 1, page 257. does some more classifications of regular versus irregular. Isn't it? It is possible that when I start now saying, okay, I've got a regular singular point. Let's make a power series. Well, the process for making my power series turns out to have a monkey wrench thrown into it by the fact that this point is singular. But there is a nice result. A result by a guy by the name of Frobenius. Technically, this result was published just a couple years earlier by a guy by the name of Fuchs, but Fuchs did not actually get that publication out to a wide enough audience, and Frobenius did, so he got credit, and everybody thought this was Frobenius's result, but Fuchs technically has priority over him. Nobody cares. Frobenius said, if x0 is a regular singular point, then there exists at least one series solution. But it doesn't quite look the way we want it to. What the hell is going on here? We have this extra factor of x minus x0 to the r pulled out in front of our power series. And r has to be known beforehand. I could, by the way, write this as Cn x minus x0 to the n plus r, if you'd rather. Put it back inside. It's your call. For some constant r, which converges, and here's the next screw up, on a punctured interval. It doesn't converge in the middle. So technically this converges on an interval minus the dot in the center. And a punctured section. Complex variables, we call this a punctured disk. Hole in the middle of my disk, I need to fix it. The problem is that I need to find R before I solve for the CJs. I need to find R first before solving for the power series coefficients. If little r is not a non-negative integer, then our solution is not analytic. We don't get a power series. We either get a function that has a root in it somehow, or a Laurent series? I may not get two different series solutions. I may only get one. I have to get at least one. And just as before, I'm going to assume almost all the time that I'm working where x0 is 0. If not, I will simply translate, do it in t, like I said yesterday. It's just going to make my life easier to do it where x0 is 0. And I'm going to do an example, except I have 4 minutes left. So I'm going to do that example tomorrow. Once I finish this example and the techniques that go with it, we're done. People, this is it. As far as I'm going. There is so much more I can do with series expansions. I'm terrible as well. What I will also say, though, is that a lot of what we do in partial differential equations, which then takes place into mechanical engineering and electrical engineering, bases itself on these numerical methods. There are lots of places where this is the basis of what we do. If you're interested in more of this, you should take the numerical methods course. We're going to do a bunch of it there. Actually, I'm not going to do it. Dr. McNabb is. I will see you all tomorrow. Have a wonderful rest of your day.
Well, I go to